virus days, keeping the kids away. On my way to where the place is closed. Can you tell me how to get to Pittsburgh Street? Six feet away until everything's a-okay. Empty desks where we used to meet. Can you tell me how to get to Pittsburgh Street? It's a very lonely ride. Everyone is stuck inside to mask people like you. Mask people like what ridiculous virus days, keeping the kids away. Social distance where we used to meet. Can you tell me how to get to Pittsburgh Street? How to get to Pittsburgh Street? How to get to Pittsburgh Street?
Where's Emily? Elmer, where's Oscar? Oh no! That's grouchy old Oscar.
Put the top of my trash can, little.
So part 2 of this, we pick up where we left off yesterday, 32, dimensional analysis, trying to turn yards into meters. So we need to cancel yards. And the question doesn't give you a tip for yards, so we need something from our mind. Yards, we could get to inches, because there's 36 inches in a yard. Then there is a tip in the story that can give us some help, because we want to cancel inches, and it's talking about inches and centimeters. The 2.54 centimeters make an inch, and then we're trying to get to meters. So centimeters needs to go, and there are 100 centimeters in a meter. So multiply all the numbers on the top, divide by the 100, and we should have it. 33 is a quick one. We have 524 grams, and then the question itself has a thing to get from grams to milliliters. So we could cancel grams and get to milliliters. The number next to the G in grams is 1.48, so we keep it there. Milliliters didn't have a number, so you could either skip it or you could pencil in a 1. We're just looking to divide those, and that should get us our answer. Keeping in mind, we always want 3 significant digits. So whatever's on your calculator screen, copy the first number, copy the second number, and at the third position, we're looking to round. 34, we have milliliters needs to go. And there's a unit in the story that can do, again, grams with milliliters. The 2.34 is next to grams. Milliliters doesn't have a number, so you could do a 1 or just leave that empty, it doesn't matter. Multiply those numbers on the top. 35, we have kilograms. Kilograms can't get you anywhere based on what's in the story. So we need knowledge in our mind that can get us from kilograms to somewhere else, most likely grams, because grams are in the story, and 1,000 grams makes a kilogram. Then we could use the grams in the story to get to milliliters, because it has 3.12 grams. And again, the number next to milliliters, either a 1 or leave it empty. Multiply these two on the top, divide by the 3.12, and we should be good. 502 milliliters, we can get from milliliters to grams from an item in the story. Canceling milliliters, getting to grams. 1.26 is the gram number, and For like the fourth one in a row, this could either be 1 or just left empty. And then we need to recognize we're not trying to get to grams, we're trying to get to kilograms. So cancel grams with the canceling top bottom match. To get to kilograms, 1,000 grams makes 1 kilogram. Multiply these, divide by the 1,000. Last one of those, we have grams. And again, grams can get us to milliliters from an item in the story. Cancel the grams. The gram number was a 0.88. Milliliters could either be a 1 or left empty, but we're trying to get to liters. So recancel the milliliters to get to liters. 1,000 milliliters makes a liter. This time we'll divide twice because there's 2 numbers on the bottom. This divide by button again for that, and that should get it for us. 38 to 42, no math, just needs some knowledge. So elements are anything on the periodic table. So the only thing in this list on the periodic table is bismuth. On the test, I probably wouldn't use bismuth again, but I'll use something from the periodic table, and that would be an element. Compound is anything with a formula. So sugar is a compound. Sugar is known as sucrose. Once upon a time, we memorized a lot of compound names and symbols, like the limes and the slate limes and the dry ices and all that stuff. Anything like that that has a chemical formula, that's going to be a compound made up of several elements. Solution is anything dissolved in water. So Kool-Aid is a solution there on this list, but that could be Pepsi or lemonade or Gatorade or anything you've dissolved in water would be a solution. Mixture, M for mixture, otherwise known as heterogeneous, or things that are made up of different things. The only one on this list made up of all sorts of different substances would be your desk. Depending on your desk, it might be wood, metal, plastic, who knows what is part of your desk. But your desk is a mixture. I could trade that for something like a TV, or my tape dispenser, or the stapler, or anything that's made up of a bunch of different things. A pen has plastic and then ink and then a little bit of a metal tip. You know, anything that's a bunch of things would be that heterogeneous mixture. Homogeneous mixture is only air, not just on this list, but it's the only one we've studied or even mentioned all year. So homogeneous mixture, I can't trade that one. That's got to just be air. 43 to 6, the differences between physical and chemical is that for chemical, a new thing is formed. For physical, there is nothing new formed. Chemical signs of chemical things happening would be like you could smell it because a gas is produced, or there's smoke, or color changes because it burned, those kinds of things. The difference between the properties versus the changes, I need to use a verb that ends in ing, like I am burning this, to make it an action. It needs to be an action verb. The properties are just going to be stated like facts, like I am able to burn this. This metal could rust, that's a property. The metal is rusting, ing verb, that would be now a change. I could cook this is different than I'm cooking it. Okay, so properties are facts, changes are action verbs with ing kind of endings. Chemical is a new thing formed, you could see the color change, you could smell it. Physical, nothing new is formed. So lead can be shaped, that's a property because there's no ing in it. And that's a physical property because when you shape lead into a new shape, it's still lead. There's no new thing formed. You can't smell it. There's no color change. There's no gas produced. None of that. Cooking, ing verb, that's a change. Cooking a turkey, you just have to contemplate if a new thing is formed. Can you smell it? Is it different afterwards than beforehand? I don't think a lot of you would eat a raw turkey, so I'm going to go with yes, a new thing is formed. I can smell the turkey cooking, excuse me. So that is a chemical change. Cutting that turkey would be a physical change. It's a change because of the ing verb again. But when you cut the turkey, you're not making a new thing formed. It doesn't like change color when you cut it. It's not like you cut it and like a gas gets produced. That's not a thing. So that's a physical change. And then gasoline can be burned. That's a property because it's a fact sentence, no ing verb. That's a chemical property though, because if you did burn the gas, it would be a new thing for them. There'd be smoke, there'd be smell, there'd be gas. 47, there's two kinds of chlorine that are getting averaged to make a mass. So what you're trying to ask yourself is, what is the 35.46 closer to? Which of the two earlier numbers is 35.46 closer to? That would be the more common one. So the answer would be chlorine 35, because 35.46 is closer to the 35-ish number than it is to the 37-ish number. 48 is some light math. Anytime percentages are mentioned, make them decimals. So 35% should be a 0.35, 65% is a 0.65, and as they almost always do, percentages like to multiply. So we're going to multiply within those pairs of numbers and then just add them up. If you do that right, your calculator will read you 38 point something. Copy the 3, copy the 8, after the decimal, you're going to have to round always in that third position, so 38.3s. And don't forget your units the whole way down the test before you turn it in. You might want to skim and just make sure you have a meter or a gram or a milliliter, or in this case, an AMD. 49's group, we're going to need a periodic table. So metals are on the left. So if you have a periodic table handy, sodium is on the left, so that is a metal for sure. Take a brief stroll, grab my periodic table. Sodium is over there in column 1, so that's a metal. Metalloids are the ones that touch the line, but aluminum's an exception. Aluminum, even though it touches the line, is a metal. So aluminum is a metal for the second one. Arsenic for the third one is a metalloid because it touches that step line, the heavy shaded step line that zigzags right through there. And then fluorine is like anything that's on the right. Fluorine's in column 17. That is a non-metal. For the next page, we're still continuing to use our table. The valence electrons is given to you by the Roman numeral. So sulfur is in Roman numeral 6, this column, number 16, Roman numeral 6. That has 6 valence electrons. Items that are more metal would either be, for 54, either toward the left or toward the lower end. So if you can find potassium and sodium, that's number 11 versus number 19. Potassium is more of a metal because it's lower. Boron versus lithium, boron is 5, lithium is 3. So lithium's more of a metal because it was more to the left. Electron dots, we're doing kind of like what we did on 53. Find the Roman numeral. Te is in column 16, which has a Roman numeral 6. That means it has 6 electrons. That means I need to make 6 dots. Maximum capacity for making dots would be 2 side by side for the top, 2 side by side for the bottom, 2 in a stack on top of each other on the right, 2 in a stack on top of each other on the left. That's not a right answer. We would do the dots like that though if we had all 8 electrons present. What we decided a second ago, because of the Roman numeral 6, is we need 6 dots. So what we need to do is erase 2 of these to keep them as balanced out as we can. So what I can't do is erase these 2, because then I have nothing on the right that keeps them balanced around the 4 sides. What I need to do is pick 1 from anywhere and 1 from anywhere else, and then I'd have 6 dots. In this case, I ended up with 1 and 1 on the right and bottom. But if I had 1 and 1, let's say, on the top and bottom, with packages of 2 elsewhere, that's fine too. We just need with 6 dots to have a 2 group, a 2 group, a 1 group, and a 1 group. It doesn't particularly matter which group is where. We just need to spread them as evenly as we can. 57, atomic number, you need to know is the number of protons. That's always a whole number. That's the numbers on the chart that are just counting 1, 2, 3, 4, 5 up as high as 111. So that number for aluminum is the 13. The atomic mass are those decimal numbers that are the upper numbers on the periodic table that count really by no particular pattern. They're usually about twice as much-ish as the atomic number, but it varies. So for aluminum, I went with 27 for my answer because I just felt like rounding it. But if you wrote 26.982, I can't disagree with that. For 59, we need to know that the noble gases are in the last column. So if we go to that last column and we find the second noble gas, helium is first, neon, Ne would be the second one. 60, you need to know that the groups are the columns. So if we're working the last column, we're still in that same area, still same place. If I want the third one, we'd be down to AR for Argon. For 61, you need to know that the periods are the rows 1 through 7. The lanthanide and actinide series don't count as rows of their own. They're within other groups, or other periods, excuse me. So 61, if I say last row, I'm looking for number 7, and I'm just coming across and finding the second one would be RA. 62, if I want a mass of 28, that's the decimal number, that's the top number. So mass of 28, I go with SI, because that's 28.0855, close enough to 28. Atomic number of 28, that's the whole number at the bottom of these squares. Whole number 28 is Ni, nickel. For 64, what we're trying to do is draw a picture of the nucleus. The protons are always inside the nucleus, so the proton count here is 27. The lower number on that 59-27 duo, that's always a count of the protons. The 59 is a count of the protons plus the neutrons. So if we do 59 minus 27, that would be 32 neutrons in the nucleus. The electrons, there's a total of 27 electrons because the protons and electrons match. But when you go to put these into energy levels, things get a little bit tricky if you need to go above level 2. Level 1 holds at most 2, and we certainly need 2 to get on our way to 27. Level 2 can only hold 8. And we certainly need 8 more, 2 plus 8, we're only up to 10 on our road to 27. But if you get to around the mix of level 3, the only way to do that is by using this chart. Because what starts to happen is you're working on level 3, after you have part of 1, you go to part of 2, and then more of 2. A little bit of 3, a little bit more of 3, but before 3 gets filled, you go up to 4. And then have to come back to 3 before you go up to some more of 4. But then you're up to 5 before you do more of 4. And even have some 5 and 6 coming into play before you finish 4. So we're going to need to use this anytime we're above level 3 because 3, 4, they start to mix. So if you don't remember how many of these held, the S's were always 2's. This S is a 2, so far I'm up to 4. P's are 6, S's are 2's. At this point, we'd be up to 12. P's are 6 again, S is 2 again. We're up to 20 total now. D's can hold up to 10. So for the story that we're presently telling and want to add up to 27, after 20, we need 7 more to go at the D level there. And that's all we're going to need to do. But we keep progressing through this if we had to get higher than 27. At this turn of a corner, we'd be at 38. At this turn of a corner, we'd be at 56. And we didn't usually memorize those numbers. We just sort of did math as we went by adding up. 2's for S's, 6's for P's, 10's for D's, 14 maximum for F's. The circles meant that 5D would not wait its turn. After 6S, the 5D would cut in line in front of the 4F to take 1 before it went back and let 4F take a few more. So like after 56, this one wouldn't take 57. This would take number 57, just 1 though. Then this would take 58, 59, 60, 61, 62, 63, 64. This could take 14 in a row before this one got another turn after it cut in line and stole its 1. 60 also cuts in line, steals 1. But anyway, back to the point at hand. where we stopped was here with the D taking 7. So at the 3 level, we have 7 from here, 6 from here, and 2 from there. 7, 6, and 2 totals 15. But we did sneak for a bit up to level 4, and level 4 had 2 in there, and that's how we're doing 64. 65, we're still using that same kind of a chart, but we're trying to add all the way up to 58. So to add up to 58, we'd have to be past this corner where the 56 was, and then do the thing that I just described a second ago. Number 57 falls to this, taking 1. And then number 58 would go to this, taking 1. And then we would just have to write out in order everything we crossed through in the order we would pass it. So 1S is first, 2S is next, 2P is next, and so on and so forth. We got as far as, let's see, 6S, followed by 4F, followed by 5D. The 5D took 1, the 4F took 1, and the rest of these were filled. S's all filled with 2's. P's all filled with 6's. There's another 2, 6. D's fill when they reach 10. And if you did all that, you did really well, but I still criticize slightly because we're supposed to separate with commas when we go from one level to another. So level 1 going to level 2, we comma that. Level 2 staying at level 2, we do not comma there. But from 2 up to 3, we comma it. 3 moves to 4, 4 back down to 3, 3 back up to 4, comma to 5, comma back down to 4, comma up, comma again, comma again, comma again. 66, Lewis structures have to do with periodic tables and dots and everything wanting to have 8. So for 66, we're trying to build a little drawing where every element will have 8 dots. I'm going to put phosphorus in the center because there's one of that, and surround it with a bunch of chlorine because there's a whole cluster of chlorine that I can put around my phosphorus. There was also a chart that showed us with electronegativities which element should go in the center, but I don't really need that here because if a P has 3 chlorines, the P is going to go to the center. So to know the dots on the P, we need to go to the periodic table. It's in Roman numeral 5, so I want to do 5 dots. A 2, a 1, a 1, and a 1. It doesn't matter which side has the 2 dots. You just need some one of the 4 sides here around the phosphorus to have 2 dots, and the others have a single dot. Chlorines come in with 7s because chlorine is in column 7. So if we want chlorine's 7 to get up to 8, we need to tack that onto the sides of the phosphorus that had 1. Because if phosphorus shares 1 with chlorine 7, chlorine has 8, and everything's happy. So chlorine there could bring its 7 like this, and now there's 8 around chlorine. A chlorine on the bottom can bring its 7 plus the 1 for phosphorus, and now there's 8 around the chlorine. Chlorine here can do about the same thing. 7 from chlorine, 1 from phosphorus, we're up to 8. And if you also look at phosphorus in the center, there's 2 on each side now. Phosphorus has 8, and that's a win. The next one, the last one of this review, is similar in the fact there's 1 nitrogen with 5 dots that could go in the center, and I could try to start the same way with 2s, 1, 1, 1s to make 5s. And then I could try to surround that with oxygens. I have an advantage on this one because the little minus means there's an extra electron. There's like a wild card that we can play anytime, but we'd rather play that last. But anywhere we fall short by an electron, the minus provides us an extra electron. This one doesn't go as well though, because oxygen comes along in column 6 with only 6 electrons. So if the oxygen comes in here with 6, and the nitrogen only has 1, that's only 7. We could try to fix that with our wild card, but then here we'd have the same issue, and we wouldn't have our wild card. And here we'd have the same issue, and we don't have our wild card. So we had a way around that in the past. Whenever we didn't feel like we had enough electrons, which is how this feels right now, The solution, the way out of this was to form what was called a double bond, where what we might have is an empty side, where up here, those two electrons, they're not helping an oxygen out very well. We'd rather try to help the oxygens out. So we could go 2 here, 2 there, 1 there, and then an empty side. And now this is going to work out a lot better for us, because if we take this oxygen and bring 6 plus 2, it has 8. Here, 6 for the oxygen plus 2 would make 8. Here, 6 plus the 1 is only 7, but we have a log card, and we can fix that issue. So if we come along with our oxygen having 6, then I could play my wild card, and I've got 8 for that oxygen. Here, I could go with 6 on this oxygen, and this oxygen now has 8. I could try to go like this. For this oxygen, I have 6 plus 2, and now I have 8, but I'm still wrong. The oxygens are good because there's 8. This oxygen's good with 8. This oxygen's good with 8, but the nitrogen doesn't have 8. The nitrogen only has 6. So for the nitrogen to end up with 8, we need for one of these oxygens to end up sharing a pair of electrons with nitrogen. It doesn't really matter which one I pick, just pick one. I'll pick this one. So if I put these 2 electrons on this side, we have a thing called a double bond. Nitrogen sharing 2 with oxygen, oxygen sharing 2 with nitrogen, double bonding. Okay, this oxygen has 8 in its world. This oxygen has 8. This oxygen has 8. But now this nitrogen also has 8, and that's a win. We need to have everything have 8. So, hope that's helpful. If you need more information, I'll get you on Zoom sometime.